Hello children, welcome back. Hopefully you had a nice break. Let's warm ourselves up by doing this problem. Make sure you guys convert the units properly. Wow, great job. So we're going to finish up rotational motion in 2 lessons. The first idea, almost everyone shows a video of like a figure skater. The figure skater has their arms like stretched out, and then they want to spin really fast to do like a triple axel or something. I don't know. So they pull their arms in close to their body, and they spin really fast. Well, I got kind of bored of that, so I'll show you guys this video instead. One more time. So it's the same idea in figure skating. This also occurs in like I guess lots of sports like diving, figure skating, maybe like skateboarding, like taekwondo, ballet, dance. If you want to spin, you have to like curl your body up into like a tight little ball. If you want to stop yourself from spinning, like in the video, the diver didn't just want to spin. They wanted to spin in the beginning, then they wanted to straighten their body out and dive into the water straight. So they stretched out their body, lengthened their body, and then they actually stopped spinning. Why? Curling up and stretching out doesn't change your mass. What does it change? It doesn't change mass, but what is changed when you stretch out? Good job, it's your moment of inertia. Hi. In the video, no, in the practice problem, there was like a rod. I think it was like 112 mr squared, but the basic formula is mr squared, which is true for a particle. And we're going to stick with that idea. But hopefully you guys remember, there's a whole table, and for different shapes, there's a different fraction that goes in front of the mr squared. Okay, so look at the particle. It could be anything, a ball, or let's say a disc. A disc of radius r is rotating with angular speed omega. Okay, let's say you're a diver, but you're not quite as skinny as the person in the video. This is me when I'm diving. Every piece of my body, this little piece of my body has mass m. Let's say that's my gallbladder, and it's moving with speed v. Yeah. So if I'm the diver and I curl up in a little ball and I'm spinning as I dive through the air, one piece of my body is moving, speed v, has mass m. It also has momentum, mv. Let's just review physics. That piece of my body also has moment of inertia times mr squared. And it also has angular velocity omega. And omega, in case you forgot, is v overall. Hopefully this blue color shows up pretty well. Who's looking at me? Momentum is mass times speed. This is the rotational equivalent of mass, moment of inertia, times the rotational equivalent of speed, angular speed. I know you already know. Wow, so smart. This is angular momentum. For some reason, I would say angular momentum, not rotational momentum. Either one's fine. And for some reason, they use capital L. I know capital L makes me feel like linear. It's not. Sorry. This is rotational momentum in a circle, not in a circle at all. But linear momentum, angular momentum. Linear momentum is how much an object is moving in a straight line and how hard it is to stop. Angular momentum is how much an object is spinning and how hard it is to stop. So, pretty much the same idea. And if you did some substitution for a particle, mr squared times v over r, in this case, should be over this on. And VR equals PR2. So that's also nice, but this is only for a particle. This is for particles, this is for everything, like disks, balls, spheres, hoops, whatever. Great. If you have any questions, definitely write them down, because I need to hear a lot of questions. This has been a long time, so if you don't remember everything about angular motion, ask me a question in class. This is great. What kind of questions did we do when we learned momentum, the linear version? We did a lot of collision problems. We often talk about collisions, and we used conservation of momentum. I have a really dumb question in my notes. It says, what happens to an object if there's no force on it? If there's no force, it won't change momentum. The same is true for a spinning object. If a spinning object experiences no torque, it'll keep the same angular speed, it'll keep the same angular momentum. Not actually true. That sounded weird, but let me show this video. An object that's spinning can change speed without net torque on it. Can you guys imagine that? Can you guys think of a situation where an object that's spinning by itself, just spinning in space, spinning on like a frictionless surface, will speed up or slow down without a torque applied? It could be crazy. How might that happen? How can a spinning object speed up or slow down without external torque? The answer is in this video.
We can demonstrate the conservation of angular momentum the same way a figure skater does by going into a tight spin. I'm not a very good skater, so I'll use this turntable and a pair of hammers. I'll hold them out at arm's length so I get nice large radius, and I'll set myself in a slow spin. I'm spinning around at a constant speed, and then I draw the hammers close to my body, and I spin around very rapidly. As soon as I move them out, I slow down again. And I can repeat this as many times as I want until the friction of the turntable stops me.
Okay, so hopefully that made sense. In torque, if the external torque is 0, there will be no change in L, the angular momentum. We always do this for collisions, linear momentum. It's true even if there's no collision. The man in the video with the big hammers, he didn't collaborate anything. He pulled the hammers in, he decreased his I, that increased his omega. Then when he extended the hammers back out, well, the hammers have a lot of mass. If he brings them to a larger radius, he increased I, that'll decrease omega, keeping L constant. So you can have a conservation of angular momentum problem without a collision. Of course, you can also have it with a collision. A lot of you guys are probably thinking of the ballistic pendulum, where the bullet hits the block, and then they kind of like swing upward together. And it's like, oh, angular momentum. Yeah, but you can't really use this to solve this problem. If you have an idea why, tell me now. This collision, you could say it's an angular momentum collision where delta L is 0, and that does work, but then it starts swinging upward and gravity pulls it down. Gravity causes torque, so then that torque is not 0. So it doesn't really make this problem any easier. You can do this beginning part with angular momentum, but the old way with linear momentum is still fine. It's not any easier or harder. So this is not really a good example. This is going to sound kind of weird, but if you use a collision, it would probably be like the same thing turning sideways. Like let's say this is a top view of you're in your bed pretending to be sick, like Ferris Bueller, a long old movie from before your time, and your mom peeks her head in the door and says, "Hey, are you feeling okay?" And you're like, "No, I'm sick. Sorry, no, can't go to school." Imagine that crazy time he's living. And she says, "Okay," and she leaves. Imagine you. This is going to sound kind of weird. Imagine you want to close the door without getting up. So you throw a ball at the door. That could be considered a conservation of angular momentum. So the door is basically rotating. It has no initial momentum. But if the ball hits it, it gains momentum from the ball. So you could solve this problem, find I for the door, and then find L for the ball, which would just be its linear momentum times R. So actually not too complicated. If the ball hit the door and stopped, you would just say PR for the ball equals I omega for the door. And since gravity is downward in this situation, it wouldn't affect the door moving horizontally. That's just an example of a problem that's possible because they're just sitting in my head doing nothing. Gravity's not somehow. Here's another example. I don't know if you guys have ever seen a potter's wheel. A potter's wheel is like a little tool they use to help them make pots that are symmetrical. So the wheel spins really, really fast. This happens in the movie Ghost, which you also never seen. And basically, since the clay is spinning in a circle, you can shape it into a nice pot really easily. And there's like a pedal to control the speed of the table. Why am I talking about this? Okay. Let's say you start the wheel before you put the clay on. So you start the wheel and you're like, oh, I forgot to put my clay on the wheel. So if the wheel's spinning, you take the clay and you place it on the wheel. What will happen to the speed of the wheel? Tell me now. If you put stationary clay on a moving wheel, what will happen to the speed the wheel turns? What's that, Bear? It'll slow down. Yeah, great job. Good job, Bear. The clay has no angular momentum. The wheel has a lot. When you put the clay on, it's a collision. You increased I for the system, so you must decrease omega. It's going to slow down when you put the heavy clay on top of it. The wheel has to slow down so the clay can speed up. Okay. I think that's pretty much it for this lesson. L equals I omega. If you understood linear momentum and you understand I and omega, it's a pretty straightforward. Hey, I think that's about it. We're obviously going to practice. I'll try to do one day, but if we need another day, we can take another day, no problem. So it's just all this stuff is also true for angular momentum. And there's one other thing that was true too. If an object changes momentum, delta p, we call that impulse, J. Change momentum is impulse. which is F times T. So try and figure out what should this equation be in angular form. Basically switch all the letters to angular and then tell yourself you're great at physics. Oh, I see. Well, if an object can change momentum when it experiences force, an object can change angular momentum when it experiences torque. This is really confusing. Looks like two T's. Yeah. Force applied for a certain time changes momentum. Torque applied for a certain time causes change in angular momentum. Angular momentum. Sorry, sit down. Yeah. Okay, so that was a great equation. I'll show you guys the last demo. I won't make you guys type in a little answer again because you guys seem to be too lazy most of the time, and some people just don't watch the videos for that reason. But lastly, so this professor, this would be a really cool demo we would do in class. If you guys want to come visit me next year around this time, I'll show you the demo because you kind of missed out. So this wheel is spinning really fast. It has a lot of angular momentum. If this man turns the wheel sideways, will it have the same angular momentum? Let's see what happens. He's going to turn the wheel left or right. What will happen to his body? What happens to the momentum of the wheel if he just turns it? He's not going to speed it up or slow it down. The wheel is pretty frictionless, so it'll keep spinning the same speed for a long time. But turning the wheel, does that affect momentum? Angular momentum? Let's find out. Why is there an Overwatch? Oh, okay. The wheel had angular momentum. It's not very intuitive, but angular momentum is not a scalar. It's a vector. And at least it can be positive or negative depending on direction. When he turns the wheel, he is changing the angular momentum. But the system is him and the wheel. So when he turns the wheel, let's say that momentum becomes more positive. That means his body has to gain angular momentum that's negative. So when he turns the wheel, it actually is very difficult. It's like a gyroscope. He has to use his muscles to turn the wheel. When he does, he's changing the wheel's angular momentum to be one way. His body will therefore gain angular momentum the other way from the wheel. So he can turn his body by turning the wheel, even though the wheel doesn't touch anything outside the system. Alright, thanks for watching a great lesson as we came back from a great break and get ready to finish off a great year. I'll see you all